Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion regarding solving linear congruences using CRT, and specifically we will focus on the uniqueness part of the solution, right. So, we want to prove that there exists a unique solution in the range 0 to bigger modulus satisfying the system of linear congruences. So, we start with some basic properties of divisibility. So, the first property is the following. Imagine you are given 3 positive integers a, b, c, and it is given to you that a divides the product of b and c, but a is co-prime to b. Then I can conclude that a divides c. Okay. That means, if a divides the product of b and c, but a is co-prime to b, then it must be the case that a divides c. And the proof is as follows. So, we know that as per the Bezo's theorem, we have integer linear combiners S and T such that I can write the GCD of A and B, which is 1 as per my premise, as S times A plus B times T. Now, if I multiply both the sides of this equation by C, I get this equation. Now, I know that it is given to me A divides the product of B and C, and hence it divides any multiple of B times C. So, it divides T times B C as well, and anyhow A divides any multiple of A. So, it will divide S times C times A, and now if I know that A divides 2 numbers, it divides the summation of those 2 numbers as well, but the summation of the 2 numbers that I am taking here is nothing but the value C. Okay. So, that is a proof of this fact. Okay. Very simple fact, but useful. Now, we prove another property which we often call as the Euclid's lemma, which is also very useful while proving the uniqueness part of the CRT theorem. So, the Euclid's lemma is as follows. It says that if P is a prime number and if it is given that P divides the product of n numbers, then definitely it has to be the case that P divides at least one of those n numbers. It can't be the case that P is a prime number and P does not divide A1, it does not divide A2, it does not divide An, but still it automatically divides the product of those n numbers. And there are again multiple ways to prove this. I will prove it using induction, because it is convenient to prove it using induction since it is a universally quantified statement for all n. So, the base case will be for n equal to 1, and which is trivial, right, because if it is given to you that P divides A1, that means P divides A1. Okay. Now, assume that the inductive hypothesis is true. That means, assume that if P divides the product of k numbers where P is a prime, then there is at least one of those k numbers which is divisible by P. I do not know which one, but it is there. Assume this statement is true for every k and every k numbers. Okay. Now, let us do the inductive step and take a new number which is the product of k plus 1 number, and imagine you have a prime number P which divides the product of those k plus 1 number. My goal is to show that there is at least one number out of this k plus 1 number which is completely divisible by P. So, the first thing to observe here is that since P is a prime number, what can I say about the greatest common divisor of P and this bigger number? So, let me call this bigger number as x. So, what can I say about the GCD of P and x? Well, the GCD will be either 1 or P, because the only divisor of P are 1 and the number P itself. There can't be any other third value of GCD. Okay. So, there are 2 possible cases. So, let us analyze those 2 cases. Now, if the GCD of P and the product of the first k numbers is 1, then from the previous result, by the previous result means in the previous slide I showed that if A divides BC and if GCD of A and B is 1, then in the previous slide I showed that it has to be the case that A divides C. So, my x is the product of first k numbers and the k plus 1th number. So, I can treat my x as A1 to AK, product of the first k. So, this is my say A, capital A, and I also have AK plus 1 also in the product, that is B. So, I know that P divides x, that means P divides the product of A and B, capital A and capital B, and I am in the case where P is co-prime to capital A, because this product of the first k terms I am calling it as A. Then from the previous result I know that P has to divide capital B, and capital B is nothing but A of k plus 1. So, that proves my inductive step, because in the inductive step I have to show that there exists at least one number which are involved in the product, which are involved here in the number x, which is completely divisible by P, and I have shown the existence of one such number. This is when the GCD of P and capital A is 1. Now, consider the case when the GCD of P and capital A is P, right. Then in that case, if the GCD of P and capital A is P, then P of course divides the capital A, and if P divides capital A and capital A is the product of k numbers, and since P is a prime number, I can use my inductive hypothesis and argue that there exists at least one number which are involved in the computation of capital A, which is completely divisible by P. That means either P divides A1 or P divides A2 or P divides AK, right. So, that proves my Euclid's lemma, important property which will be again useful. So, now coming back to the uniqueness proof part for the Chinese remainder theorem. In the last lecture we showed that there exists at least one solution in the range 0 to m minus 1. How do I prove that there is no other solution possible satisfying the same system of linear congruences and which is also in the range 0 to m minus 1? We have to refute the existence of second solution. So, again we will take the help of a helping lemma, and this helping lemma will be useful later as well. So, what this helping lemma says is the following. Imagine you are given n moduluses which are, I forgot to write here, which are pairwise relatively prime. That means, you take any pair of moduluses mi and mj, they are co-prime to each other, and suppose you know that you are given two numbers a and b which are congruent with respect to all the n individual moduluses. It means, they are congruent with respect to modulo m1, they are congruent with respect to modulo m2, they are congruent with respect to modulus m3 and so on. Then the claim here is that the same two numbers a and b are congruent with respect to the bigger modulus m, which is the product of all the n moduluses. And again there are multiple ways to prove this. Let us follow the following strategy. So, as per the fundamental theorem, I know that this bigger modulus big M must be having a unique prime factorization. That means, I can express this bigger modulus M as product of powers of prime. So, let those powers be E1, E2, EQ and so on. Okay. Now, my goal is to show the following. In my proof, I will show that if I take the prime power factorization of a minus b, right. So, a minus b also will be a number and it will have a prime power factorization. So, I have to so let the prime power factorization of a minus b be p1 times E1 bar, p2 times E2 bar E2 prime, and like that PQ times EQ prime and so on. So, what I want to show is that each of the prime factors which were involved in the prime factorization of m, they are also involved in the prime power factorization of a minus b, and with at least the same individual powers with which they were involved in the prime factorization of m. So, what I am trying to say here is the following. Say for instance, if my m was say 2 to the power 3 and 3 to the power 1 and 4 to the power not 4, 5 to the power 6 and so on. Suppose these were the various powers of primes which were involved in the prime power factorization of m. My goal will be to show that if I consider a minus b, then the same prime factor 2 is involved at least 3 or more than 3 times. That means, it will be either greater than equal to 3 power. It is must, that means 2 should have 3 or more power appearing in the prime factorization of a minus b. Similarly, the factor 3 should appear with the power at least 1. The next prime factor 5 should appear with at least power 6 and so on. If I show this, then that shows that a minus b is completely divisible by m. This will, if I show this, then this will imply that a minus b is divisible by m, and that is what precisely I want to show. I want to show a is congruent to b modulo m, and remember an equivalent definition of congruence is that if a is congruent to b modulo m, then that also implies a minus b is completely divisible by m. So, if I can show that each of the prime factors which were involved in the prime factorization of m are also involved in the prime factorization of a minus b, and with at least the same powers with which they were appearing in the prime factorization of m, that means a minus b is completely divisible by m, and that is what the proof strategy will be. Okay. So, let us consider an arbitrary prime factor of the bigger modulus m, and suppose it is appearing with power e in the prime power factorization. That means, so m is equal to 2 power e1, 3 power e2 and so on, and some p power e and so on. So, I am taking an arbitrary prime which is appearing with some power in the prime power factorization of m. I have to show that the same power at least is also present in the prime power factorization of a minus b as well, right. Now, since p is occurring with power e in the prime power factorization of m, that means I can definitely say that p divides the product of m1 to mn, right, because m is equal to, m involves a prime power of the form p power e in its prime power factorization. That means, p has to divide the product of m1 to mn, which is nothing but m. Okay. That means, this condition holds, and now I can apply the Euclid's lemma, which I just proved some time back, that if p is a prime number and if it divides the product of n values, then it has to divide at least one of those n values. So, that means, p divides at least one of the small moduluses, so call it as mi, and I know that p does not divide any other modulus mj. I can conclude that, because I know that the various moduluses m1 to mn, they are pairwise prime. That means, there can't be any other modulus mj such that p divides at other modulus mj as well, because if p divides the other modulus mj as well, then I already have the fact that p divides mi, and if p divides mj as well, then I will get the conclusion that there is a common divisor other than 1, namely the prime number p, which divides both mi and mj, and which goes against the assumption that my moduluses mi and mj are pairwise prime, right. And if p does not divide any other modulus mj, and I know that p power e is occurring in m as in the prime power factorization, then the only way the contribution p power e can come in the prime power factorization of m is because the p power e was contributed in the prime power factorization of mi itself. So, remember each of the moduluses m1, m2, mi, mj, mn will individually have their own prime power factorization, and I have the product of all these moduluses, which is m. I know that p power e is contributed in the prime power factorization of m. So, this p power e might be accumulated to several moduluses m1, m2, mi, mj, mn, but what I have shown here is that p, if at all p is coming from mi, that means if p's contribution was there in the prime power factorization of mi, because if p divides mi, then p will not be appearing in the prime power factorization of m1, p will not be appearing in the prime power factorization of m2, p will not be appearing in the prime power factorization of mj, p will not be appearing in the prime power factorization of mn, and so on. So, that means the only way this p power e would have been accumulated in the prime power factorization of m is because it was present in the prime power factorization of mi itself. Okay. So, that is a conclusion I have drawn, that p power e occurs in the prime power factorization of mi. Now, remember the properties of A and B is the following: they are congruent with respect to every modulus, that means A minus B is completely divisible by all the n individual moduluses. So, A minus B is also divisible by mi as well, because as per my premise A and B, they are congruent modulo mi as well, the same mi where p power e occurs in the prime power factorization. Okay. That means p power e occurs as a prime power factorization in the prime power factorization of mi, and if mi divides A minus b, that means p power e also occurs in the prime power factorization of A minus b as well, and that is what precisely I wanted to show. Okay. So, namely if I substitute p with p1, I have shown that p1 power e1 will also occur in the prime power factorization of A minus b. If I substitute p with p2 in this whole proof, then I concluded that p2 power e2 also occurs in the, at least p2 power e2 also occurs in the prime power factorization of A minus b, as so on. That means p2 can occur with higher power as well, but at least p2 power e2 is definitely there, that much power is always there in the prime power factorization of A minus b, and so on. Okay. So, we have proved the helping lemma. Now, coming back to the proof of the uniqueness of the solution, we wanted to prove that there is a unique solution x in the range 0 to m minus 1, satisfying the system of n linear congruences. So, we will prove it by as follows. So, on contrary, imagine you have two solutions in the range 0 to m minus 1 satisfying this system of linear congruences, and those solutions be let x and y. That means, x satisfies this system of n linear congruences, that means, x is congruent to A1 modulo m1, x is congruent to A2 modulo m2, and x is congruent to An modulo mn. And similarly, since y is also a solution for the same system of linear congruences, this set of n linear congruences will also get satisfied. Now, from the first equation here and the first equation here, I get that x is congruent to y modulo mk, or x is congruent to y modulo m1, right, because x minus a1 is completely divisible by m1 and y minus a1 is completely divisible by m1. Then what can I say about x minus y? So, if x minus y, if m1 completely divides x minus y, and if m1 divides x minus a1 completely, that comes because of the first linear equation here, linear congruence here, and this linear congruence tells me that m1 divides y minus a1, then I can say that m1 divides the difference of these two numbers as well, and the difference of these two numbers will be x minus y. In the same way, I can say that x minus y is completely divisible by m2. I can say that x minus y is completely divisible by mk, and x minus y is completely divisible by mn. So, I get n congruences like this, that means x and y are congruent modulo m1, m2, mn, and remember that my m1, m2, mn, they are pairwise relatively prime. So, I can take the help of helping lemma and I can conclude that both x and y are congruent modulo m. And since both x and y were in the range 0 to m minus 1, that means they were strictly less than m, and both of them are congruent, then that is possible only when x is equal to y. Okay. So, that shows that there exists a unique solution modulo m satisfying your system of linear congruences. So, now let us see an example for Chinese remainder theorem. So, say we want to find out this unknown x satisfying this system of linear congruences. So, we will find out the bigger modulus and the sum moduluses. So, the bigger modulus will be the product of 3, 5, 7, and you can see your m1 is small m1 is 3, small m2 is 5, small m3 is 7, and a1 is 2, a2 is 3, and a3 is 2. Okay. So, my bigger modulus will be 105, m1 will be the product of all the moduluses except 3. So, 35, m2 will be the product of all the small moduluses except 5, and m3 will be the product of all the 3 moduluses except 7. So, I found m1, m2, m3. Now, my next goal will be to find out m1 inverse modulo small m1, m2 inverse modulo small m2, and m3 inverse modulo small m3, which I can do by using using extended Euclid's algorithm. So, m1 inverse modulo small m1 will be 2, because you can see that your m1 is 35. If you multiply 35 with 2 and then you take modulo small modulo m1, then you will get the answer 1. In the same way, m2 inverse modulo small m2 is 1, and m3 inverse modulo small m3 is also 1. So, then as per the Chinese remainder theorem, we will compute the value x, which is the linear combination of your a1 and which is the linear combination of your a1, a2 and a3, and the linear combiners are the various m1, m2, m3 and their respective multiplicative inverse multiplied with each other. Okay. So, this will be the value of x. Now, this x will be 233 modulo 105. So, our goal is to find out the unique solution. So, of course, 233 is a solution. If I take x equal to 233, you can verify that it satisfies this system of linear equation, but we want to find out a unique solution in the range 0 to 104. Okay. So, how I can do that? I can keep on subtracting 105, or equivalently I can directly take 233 modulo 105, because that will tell me exact number of times 105 have to be subtracted. So, that I get a remainder within the range 0 to 104, namely 23, which will be a solution for the system of given linear congruences. So, now let us see some application of Chinese remainder theorem. It has tremendous applications of course in cryptography, but in general it has other applications, and the main application is when we want to do arithmetic with large values. So, what basically CRT tells us that if you are dealing with very big moduluses and you want to do arithmetic involving those big moduluses, then instead of doing operations modulo those big moduluses, you can do operations modulo small moduluses and they will be equivalent. What do I mean by that? So, imagine you are given n moduluses m1 to m1 which are relatively prime, and you are given a bigger modulus capital M, big M, which is the product of these n moduluses. So, consider the set Zm. This set Zm is nothing but it has all the integers 0 to m minus 1, and you have n number of small sets here. You have Zm1, Zm1 is nothing but you have all the integers from 0 to m1 minus 1. Zm2 has all the integers from 0 to m2 minus 1, and Zmn has all the integers from 0 to mn minus 1. We will later encounter these sets again. Now, what Chinese remainder theorem basically tells you, it establishes a bijection between this bigger set Zm and the Cartesian product of these n sets. What exactly is the bijection? The bijection is the following. If you are given a value a here and you want to find out the corresponding mapping as per this bijection, then the mapping then the image of A is obtained by computing A modulo m1, A modulo m2, A modulo mn. That will be the representation of A, and my claim is that this representation that we have obtained is an injective mapping, because if you have two different values A and B, where A is different from B, then definitely there will be at least one mi where A modulo mi and b modulo mi will be different, because if A modulo m1 and b modulo m1 is same, A modulo m2, b modulo m2 is same, A modulo mi, b modulo mi is same, and A modulo mn and b modulo mn are same, then using the, and since my modulus is m1 to mn are pairwise relatively prime, using the helping lemma that we have just proved, we come to the conclusion that A and b are also congruent, namely they are same, because both A and b are in the range 0 to m minus 1. So, you can't have two different values A and b and at the same time their representations are also same. By the way, by representation I mean now each value in the range 0 to m minus 1 or an element of Zm will be now represented by an n tuple. Okay. So, why n tuple? Because there will be n values which will be treated as the representation of A. So, that is an injective mapping, and the mapping is surjective as well, because if I give you arbitrary values of A1, A2, An, where A1 is in the range 0 to m1 minus 1, A2 is in the range 0 to m2 minus 1 and An is in the range 0 to mn minus 1, then I can find out the corresponding A in the range 0 to m minus 1, whose CRT representation will be A1, A2, An. Okay. So, that shows that my mapping is surjective as well. So, basically what I can now say is the following. If you are given two numbers A and B and their corresponding representations, that means now any operation which you want to do in the bigger set modulo the bigger modulus, that can be equivalently performed in the smaller worlds modulo the small moduluses, modulo m1, modulo m2, modulo m1. So, what you have to do is you have to focus on the first component of the representation of A and B. They will be in this set. You perform the same operation which you want to perform in the bigger set and do modulo the small modulus. You perform the same operation in the second world modulo m2, you perform the same operation in the nth world modulo mn and so on. Okay. And same holds for product as well. That means, what it's equivalently what it shows is that using CRT, any arithmetic operations which you want to perform over integers modulo some bigger modulus, that is equivalent to performing integers that is equivalent to performing arithmetic over the remainders as well. Okay. And this is a very interesting fact which we use extensively, at least in cryptography. Okay. So, for instance, if your say M1 is an each of these moduluses M1, M2, Mn, they are n bit prime numbers. Okay. Then my capital M is an enormously large value. Now, if I want to add a plus b, if I want to do a plus b modulo that enormously large modulus, then it will be an overkill. Instead, what I am saying is that you perform a plus b modulo several small moduluses, and that will be the equivalent representation of whatever remainder you would have obtained by adding a and b in the modulo the bigger modulus, right. So, that gives you a tremendous saving in the computation that is involved. So, that makes CRT a very interesting theorem. It has got tremendous application, especially in cryptography. So, with that I conclude today's lecture. These are the references, and just to summarize, in this lecture we continued our discussion on the Chinese remainder theorem, and we proved that indeed there exists a unique solution modulo the bigger modulus satisfying the given system of linear congruences. Thank you.